My name is Eduardo Bañados. It's a pleasure to be here. First time in Hawaii. Very exciting. I'm hoping I don't block the people watching this over video. Yeah. So I'm a Carnegie Princeton fellow, and today I'm going to talk about quasars in the epoch of reionization. I know that quasars and epoch of reionization are very specific topics, so I'm going to try to zoom out and keep the big picture. So probably here there are quasar experts, but probably there are people that don't know much. So I'm trying to cover everyone here. But if it's so, don't hesitate to stop me at any time if you have any questions. So let's start with the big pictures. I'm pretty sure all of you have seen a cartoon like this with the history of the universe. On the left, we have the Big Bang. Then we have the combination, the dark ages. There were no sources of light until at some point the first stars, the first galaxies, the first quasars start to appear. They start to reionize the universe. And that happens in the first billion years of the universe. Then time goes by, and about 13.7 giga-years after is us. Right, so the universe is big, and in this talk, I'm just going to focus on this particular region of this diagram. So the first billion years, particularly the epoch of reionization. And during this talk, I'm gonna be talking like back and forth between time and redshift. So for you to just have this in mind, that when I say redshift 6, that means when the universe was about 1 billion years old, or 1 giga-year. And reionization is one of the current frontiers of research. So now we are finding galaxies all the way when the universe was less than 1 billion years old. But so far, most of these galaxies are really faint. So we're finding them with JWST, with a lot of effort of the community. But they are so faint that at this point, we basically can identify them. Sometimes it's really hard to even spectroscopically confirm them. And that's why the community is making a huge effort to build the next generation of telescopes like JWST and the next generation of 30-meter telescopes. The hope is that we can characterize these very distant galaxies, some of the first galaxies that form in the universe. In this talk, I'm going to focus on other objects that are quasars. The quasars are the most luminous non-transient objects in the universe, so we can study them very far, also in the epoch of reionization, but with the current facilities. So I've been mentioning reionization a few times now. So now it's time to zoom in a little bit. I'm going to spend one more slide to zoom into the reionization epoch. As it says here, it's one of the, what is the last major phase change of our universe. So let's spend one more slide on that. So this plot shows the state of the art on reionization constraints. So there are two things that we know. After recombination, the universe was basically neutral, and now we live in an ionized universe. So one of the fundamental questions is how this process happened, right? So here in this plot, I'm showing neutral fractions. So 0 is completely ionized and 1 is completely neutral. And these are the best observational constraints we have so far, mostly coming from the cosmic microwave background and isotropies that give us an average redshift or time when this process happens, and also a duration. And the other is coming from studies from very high redshift quasars, like my alpha forest. I'm gonna talk about that in a few slides, that put the constraints on the end stages of reionization. So because of quasars, we know that the universe has to be mostly reionized by redshift 6 or within the first billion years. So this process, even though we have some constraints, these constraints are not very tight. And this has profound consequences on how the universe evolves after that, how the galaxies evolve, and how basically we end up here ourselves. And here observations and simulations go hand in hand. So with observations, we can put constraints on how this process occurs, but then we need simulations to try to understand physically how this process happened. For example, if you had that the main contributors to reionizing the universe were massive galaxies or faint galaxies, the shape of this curve will be very different. But with the current constraints, we cannot, well, you can basically reionize the universe in many different ways. So one of my main motivations is observationally trying to constrain this better. And I'm going to go back to this at the end of the talk. So hopefully that's clear why I think reionization is important and why we should care. But this is also a quasar talk, right? So I guess I need to spend a few slides also telling you what a quasar is. And in particular, I wanted to show you at the very beginning a rest frame UV optical spectrum of a quasar. So this is an artistic representation of what I think they are. So these are supermassive black holes in the center of galaxies that are accreting material, and that material heats up, forms this accretion disk, and emit a huge amount of radiation. And when you take a spectrum of this object like this is what you get. So this flux versus wavelength. And basically you see that there's this power law continuum emission, and on top of that, you have these broad emission lines, lemon alpha, carbon 4, magnesium 2, that are coming from high velocity clouds very close by to the quasar. And measuring this emission line, the shape and the continuum, you can actually get an estimate of the black hole that is in the center of this massive galaxy. So, but when we're looking at this, so what I'm showing here now is a spectral energy distribution of quasar. So when we look at the rest frame UV optical, we're basically seeing light coming from the very center of the system, very close to the black holes from the accretion disk. And when we go to longer wavelengths, we start to see different parts of this galaxy system, right? So it's a quasar, but it also lives in a galaxy. And when you go all the way to the far infrared, now the light from the host galaxy starts to dominate the cold dust, and you can study the galaxies where this object live more easily. And I'm also going to talk about that a little bit in my talk. And another topic, why quasars are important. So there are many reasons why these objects are interesting, but while they are important tools to prove the intergalactic medium, or IGM. So here I'm showing two examples of quasars at different redshift. So the one at the top is redshift 0.16. This was the first quasar discovered. It's one of the closest ones. And then we have a quasar at higher redshift, 3.62. And this is the Lyman alpha line that now you're all familiar with, I showed in the previous plot. And you see that these objects look very similar, except Luar of Lyman alpha, where the one that is higher redshift or more distant has these very strong absorption features. That's what we call the Lyman alpha forest. And this is relatively simple to understand when you think these objects are very far. And if the object is farther away, the light has to travel more to reach us. And in its way, it will encounter galaxies, molecular clouds of neutral hydrogen, and all of that information is imprinted in the quasar spectrum. So they are powerful tools because we can have an idea what is between us and the quasars. And now if you take this to the extreme, and you go all the way to redshift 7, a quasar spectrum looks like this. And this is a Jenner spectrum of one of the most distant quasars known. And basically what I find remarkable is that if you ignore what is Luar of Lyman alpha, these objects look basically identical to a quasar redshift 1, 2, 3. So if I didn't give you the wavelength and only the shape, you wouldn't know what redshift the object is. And of course, then Luar of Lyman alpha, you have complete absorption, because now we are, well, the object is very far, and there is also a considerable amount of neutral hydrogen there absorbing all that UV flux. So in the same slide, we have one of the closest quasars and one of the most distant quasars. And they're important tools for studying the IGM. And the last point I want to mention in this introduction is that quasars live in galaxies. I already said this, but I think I find it's always good to emphasize this, because I always go to conferences and they say, well, you study this very weird object, which might be true, but they live in galaxies. And we know that was one of the key roles of JWST, to show that these point sources live in galaxies. Now, the quasars that I'm studying, these very distant quasars, we can measure the black hole masses. And we know there is a relation between the black hole mass and the stellar mass or bulge mass. There are very flavors of this correlation that now we know exists, but has probably more scattered than we initially thought, but there's still a correlation. So the objects that I'm studying, all of them, we can measure black hole masses from the emission lines, and they're all very massive. So they are the high end of the black hole masses. And because of this relation, we also expect this object to live in massive galaxies. Until recently, we didn't have a good data to actually test this, but this is the expectation. And when you look at simulations and you find these very massive galaxies, they usually sit in the center of peak of dark matter distribution. And if you look at simulation and took those peaks and make them evolve, they tend to evolve in the galaxy cluster that we see nowadays. So people think that these objects might live in some special environments. So we can also study the galaxy, but it's also interesting to study the galaxies where these very distant quasars live. Right. So this is basically the three topics that I thought would be good to highlight at the very beginning. There are many more, would be a whole talk for this, but I'm also going to focus the next of my talk on these three topics. So first character that we can use these quasars, not only to study the central black hole, but also to study the galaxies where they live. I think this is important because, well, we have, as I said, the quasars are these accreted supermassive black holes, accreting material, and at some point, that material is going to run out, the quasar phase is going to finish, so there's not going to be a quasar anymore, but the galaxy is still going to be there. And we should take advantage of this to also study this galaxy that maybe if we were not seeing this active phase, it would be very hard to discover without the help of the central black hole. As I said, also it's very interesting to study what the environments these objects live. And at the end of the talk, I'm going to come back to the first part of the talk, see how we can use these objects to constrain the intergalactic medium. But so hopefully I convinced you that these are interesting objects, these quasars in the epoch of reionization, the first billion years of the universe. There are many things you can do with them, with current facilities like Gemini, but you cannot do anything of this if you don't know where they are. And that's one of the first challenges. And this is not straightforward. This is probably harder than finding the needle in a haystack. So redshift 6, these objects, these bright quasars are very rare. So you expect to find less than 1 per cubic gigaparsec. So if we put that in for an observational astronomer, it's less than 1 per 100 square degrees. So you can go very deep with HST, go to magnitude 55, and you won't find any of these objects unless you're very, very lucky. So to find these objects, you really need to go wide and have hopefully multi-wavelength information. And we live in an era that there are many of these surveys that actually allow us to do this very successfully. These are some examples of this. So as it says, Pan-STARRS, Dark Energy Survey, HSC, WISE. And here I'm highlighting the Pan-STARRS database that is based in Hawaii, because I spent a large fraction of my PhD thesis mining that database to try to find these very distant quasars. And nowadays, I'm basically using all these surveys and even more to find for these rare objects. So I just want to give you an idea, a simplified idea how we do this. So this is, what I'm showing here is wavelength. So this is, again, a quasar spectrum of redshift 5. And I'm overplotting the Pan-STARRS filters, the I, Z, and Y. And on the left hand, you have a color diagram, Z minus Y, I minus Z. So the flux of this object in this bands. And this point here represents the color of this particular object. So what we do to find these objects is not something new. Maybe you're familiar with the Lyman-Brecht technique, but it's just taken to higher redshift. Now, if you shift this template of a quasar spectrum to higher redshift, you can, again, repeat the experiment, measure the color, and in principle, we know where this kind of objects live in a diagram like this. This is one of the diagrams used. I'm using multicolor, but gives you the basic idea. So in principle, because we know the shape of the quasar spectrum, we know where to look for them. And if you want to find the objects that are most distant, you just simply do a color cut there, and you get all the quasars over redshift 6, and there you are done, right? So in principle, it's true, but there are some complications there, right? So these big surveys, we are basically at the limit of their detection. There are a lot of contaminants that are not astrophysical, so that's one of the main challenges to remove. But even if you are very good at removing those, there are other astronomical objects that also have very similar colors than these quasars, and these are brown dwarfs, especially M, L, and T dwarfs. So these objects are faint, red, they look like quasars, but they are much more closer than us. Basically, these are in our galaxy, and they are 1,000 times more numerous or more. So in principle, this is what we do, and then we have to find smart ways to how to remove these large surveys, non-astrophysical objects and brown dwarfs. I call them contaminants, but no, they are interesting for many of you here. So I have many new ones if you want to talk to me. Yes, and I'm not the first one, I'm not the only one trying to do this. So people have been looking for these objects for decades, and it was not until the year 2000 that we found the first quasar within the first billion years of the universe, and that was when SDSS came online. So in year 2000, we had one. And if we go 10 years later, 2011, we had about 60, and you see that it was not only SDSS, there started to be other surveys that were trying to look for these objects, and 2011, there was a big leap on redshift to redshift 7.1. This is the quasar I showed you in the very beginning. And I'm also fast forwarding here because here's when I started my PhD. And if we go now to today, this plot looks like this, and it's not updated. This is updated March 2017, but I just wanted to show you that over the last 3-4 years, there has been a boom, mostly coming from the Panther survey, that we have more than double or almost triple the number of quasars in the first giga year of the universe. And these are in red. Well, in red, I'm painting here the ones that we have discovered, but also the ones that we recovered from the other surveys. So this is a summary of where the state of the field is, again, updated in March 2017. And one of the good things that I want to highlight here is that now we have basically quasars all over the sky, or mostly all over Pan-STARRS coverage. But that's very important, because before our survey, basically most of or all of the quasars known at these distances were in the northern hemisphere. And we know now that there are amazing facilities in the south, like ALMA, that didn't really have quasars to follow up. So now we have actually many of these objects that are to the reach of the powerful telescope in the southern hemisphere too. And this is just to give you an update to today, this month. So this in red now, I'm painting all the quasars that I played a role in their discovery. So more than half I've helped to discover. And you can see here now we have a new record redshift quasar, as I mentioned in my abstract. But I'm going to talk about that object at the end of the talk, so don't leave. Yeah, and now the Pan-STARRS sample is looking more or less like this. This is really hard to read, have many more of these plots. But when you have a large sample of these objects, you can play some games, you can do some stacking. And this is what I started to do, right? So what I'm showing here in the bottom is a composite spectrum, so the average of 100 of these Pan-STARRS quasars. And the dotted line, the dashed line is a quasar redshift 2, typical quasar, and you see again, lower Flyme alpha, they look the same. Lower Flyme alpha, you see this breaking flux. And then the blue one is the stack of the 10 objects with the weakest emission lines, and the one in top with the strongest emission lines. So even though they look similar, there is a variety. So there is a family of these objects with different properties. And we knew this, but this just came as a surprise, at least to me, especially these objects here that have very weak emission lines, and not only Lyman alpha, also carbon-4, that we were finding too many of these objects. And these objects, even though they exist, a lower redshift, they are very rare. So they make between 1 to 6% at redshift 2 or 4. And we were finding that about 15% of these objects exist at redshift 6. And I still don't have a good explanation for this. And people have been thinking hard enough since the discovery to try to explain these objects with very weak lines. And there are many possible scenarios, probably related to the broad absorption line. So there's something going on very close to the quasar. I think these are all possible explanations. I like this one in particular that says that it's an evolutionary process, that all quasars at some point, when they're very young, they are still forming the broad emission line, and you don't have very strong high excitation lines. I don't have a very good reason why I like that one, other than because we're seeing more of these objects at redshift 6, when in average, I think we're looking at a younger population because they have a limited time to form. So maybe we're seeing something related with that. But still, really, this is a puzzle that just came for free, and for having this large sample. And if you have further ideas how we can solve this puzzle, let me know. But yeah, so I'm gonna move on from the discovery. Now we know that we actually have more than 200 of these very distant objects. We had 60 a few years ago, so now we can actually try to do some characterization of the population. And I'm going to go back to quasar host galaxies. So I showed you this plot at the beginning. I told you that when you go to the far infrared, then the dominant source is the host galaxy, the dust coming from the host galaxy, not the accretion disk. So this is far infrared, and when we go all the way to redshift 6, the far infrared is shifted to the millimeter band. And we have now powerful telescopes that can look exactly at that regime, like ALMA. So here we're going to be talking about particular dust continuum, that is star formation tracer. And I'm going to also emphasize on the C class or C2 158 micron line for several reasons. One of the main reasons is one of the brightest line in star forming galaxies. So that's good when you're trying to detect something very far redshift. You just go for the brightest one first. But it's a very interesting line because it's a star formation tracer and also give us a very accurate redshift estimate. But this line is really bright, okay? So we could do this even before ALMA. So this is a 3.5-hour spectrum with the PDBI or NOEMA interferometer in France. And you can see that we have a very nice detection of C plus and even water on a quasar redshift 6.5. So this was possible before the ALMA era in a reasonable amount of time. But this object was handpicked. So this is the brightest quasar known about redshift 6.5. And there are another few other objects that had also similar measurements with PDBI before ALMA, but they all were the extreme of the extreme objects. So all my quasars are very extreme, but these were just the very tip of the iceberg. And we wanted to see if the host galaxies where they live were also extreme, and that's what we found. But again, so these were interesting but very biased studies.
Question.
Yes.
Presumably, the correlation between the quasar brightness and the brightness of this line, which is emitted way out in the galaxy, must be a very rough correlation. So you could find a strong line in some other quasar which isn't as bright, right?
Yes.
You just chose the brightest one because that was the best chance. But
yeah, exactly. And yeah, you need to convince the tag that you will find something. So that's the best chance to get the tag excited. Yeah. Probably write a paper about that. But now with ALMA, this is changing, and because it's more powerful, as I'm going to show you in a few slides. But ALMA now is finding, well, this one was 20 millijanskis. This is one of the most distant C+ detections all the way to redshift 7.1. This only 3 millijanskis, but you see this is beautiful, and this is much higher resolution too. So this is 0.2 arc-second resolution, and this particular quasar, one of the most distant we know, even with 0.2 arc-second resolution, that's a kiloparsec, redshift 7, is unresolved. But now with ALMA, we are doing this in a larger sample, and not only choosing the most extremes. Still, again, these are all extremes, but only now we're making a less strict requirement. Now we are studying these objects in about 30, 40 of these quasars, and these are the properties that we're finding. So now with ALMA, some of them we can measure some rotation, some dynamics, and they show a variety of properties. This is just a summary, but in summary, they are very massive. So dynamical masses of 10 to the 10, dust masses of 10 to the 8. So these are really, really massive galaxies that have a range of sizes. They're all very compact. Some of them are still unresolved at 1 kiloparsec resolution, like this one. Some others are resolved and they have a size of 3 kiloparsecs. So there's a variety there, but they're all forming stars really like crazy. So just to have you this in your mind, if you take the Orion Nebula, take that and spread that over kiloparsec scales, those are the kind of monsters where these objects live. So those properties I just showed you before are not coming from that one quasar, but it's coming from a sample. I told you when ALMA came online, we submitted a proposal to try to study the host galaxies of a large sample of these objects. So we submitted for 35 quasars. At the end, 27 got observed. And these are really, really, well, this here, hopefully you see, these are positions of some of those. The take-home message here is that we basically detect the host galaxies of all of these objects, and in only 8 minutes. Only in 8 minutes with ALMA, you can detect some of the most distant galaxies we know, which I think is really phenomenal. And all of them in C+, and some of them also in continuums, so-called dust. And they show a range of properties that's summarized in the previous slide. And I'm coming back to this ALMA survey in a few slides.
So how large is that survey?
That was it. So it was 35 objects and 27 got observed.
Yeah, but what's the sky coverage?
Tiny. So the field of view of ALMA is 20 a minute, 20 seconds.
Oh, so they were targeted.
Yeah, we chose the quasar that we visited from ALMA that required that we had a very accurate redshift from magnesium 2. Yeah. So these are not new quasars. We are following up some of the quasars that we just discovered before. And all the quasars I showed you in red before, they are all spectroscopically confirmed. Just need to keep track of my time. Fine. And I'm coming back to that slide in a few more, but I also want to probably very quickly talk about the environment of these objects. So I told you that they might live in interesting environments. So when you look at simulations and see where these massive galaxies are known, we have some evidence that they're actually very massive and have very massive black holes. And you look at simulations, this is a simulation what you expect of an environment of a high-redshift quasar, and you expect them to live in overdensities on megaparsec scales, and then if you make them evolve to redshift 0, they end up being galaxy clusters. So this is the expectation, but observationally, this is still inconclusive. So there have been, since the discovery of these objects, people have tried to test for this and see if you find overdensities of galaxies around these quasars. And most of these studies, especially at the beginning, were focusing on Lyman break galaxies, so galaxies that were detected in the same way as the quasars. Some studies found overdensities, some studies found that you couldn't distinguish between a blank field or a quasar field, and some others even underdensities. But the main problem with that is that this technique has a very large redshift error. So it's a delta Z of 1. So even if you find an overdensity, you are not quite sure if it's related to the quasar or not. So I tried to tackle this problem in a slightly different way. And I was looking for Lyman alpha emitters. So Lyman alpha emitters are these star-forming galaxies that have a very strong Lyman alpha line. So you can put a very narrow band filter there and select galaxies that are at redshift very close to the quasar. So this is not a new idea, right? So people have done this at redshift 3.1, 2.1, but it was the first time done on a quasar at redshift 5.7. And there's a simple reason for that. So the sky in the near infrared is very bright, and there are only certain wavelengths where you can put a narrow band filter and do this. And until recently, there were no quasars known at that specific redshift. So we found one, we did the experiment, and we basically found that we cannot distinguish the number of Lyman alpha emitters in this quasar field from a random field. And of course, that was based on a sample of one. Maybe we were unlucky, maybe these objects don't live in the most massive dark matter halos, maybe we need to survey larger areas. There are many reasons. It was puzzling, and so this year I repeated this with Akira Matsukeli, a PhD student at MPIA, in a different field, and we found basically the same result. So we don't find any evidence that these objects live in very overdense environments of Lyman alpha emitters, which is puzzling, but yeah, so maybe these objects don't live in overdensities. But this brings me to, again, to this ALMA C+ survey that I told you that what is being very successful. So basically, all objects that we observed in 8 minutes, we got a detection. So we're super happy with that. That was the plan of the program, and it's working. But I told you that it was about 100% C+ detection, and it was about 100 because it's actually more than 100. So in some fields, we found some companions to this quasar in this tiny field of view, right? So 20 arcseconds. Hopefully you can see this. So here we have some quasars, and there are companions very close to the object. So in physical scale, these are between 8 and 15 kiloparsecs away from the quasar, and they are all at very similar redshifts. So here you're seeing the C+ spectrum of the quasar and the companions. So these objects are projected separations very close. The velocity offsets are small, and sometimes these companions are even brighter than the quasars. But they appear only in ALMA, and they don't appear in any of the other follow-up images we have. And I have to just show you this. This is one of the companion systems I show you. So this is, think of this as a long slit spectrum. So this spatial offset, velocity offset, this is the quasar position, the companion position. And in this particular case, in 8 minutes, you see that they are connected. So I think this might be one of the most distant, if not the most distant evidence of a merger. And again, this is only 8 minutes integration time. So these systems came for free, right? So we were not expecting for them, and they were a surprise for us. And so now we're trying to understand them better and doing all kind of follow-up we can. I'm the PI of an ALMA, an HST, and Chandler follow-up of these systems. And for example, this is work in progress. This was the original data, 8 minutes, and this is one example of one of these objects with 45 minutes and higher resolution. And now we can even see velocity maps of the companion galaxies. We're finding more emitters because the data is deeper, but at different redshifts, but still interesting. So keep tuned with that, because I think there are many more results coming on this interesting object. So what's going on here, right? So I was telling you that we don't find overdensities of galaxies, of lemma familiars on these objects, and now with ALMA we're finding these close companions. So maybe these objects live in overdensities after all. Maybe we were looking at the wrong population, and we need to find these dusty star-forming galaxies. But it's hard to tell, especially because the ALMA field of view is tiny again, so it's kiloparsec scales. And when these simulations predict that the overdensities are in megaparsec scales, and try to prove that with ALMA is just too expensive, right? So maybe we're seeing evidence that there are overdense environments, but maybe we're just seeing how the process that this black hole formed, right? So they need mergers. So maybe this is just very central, and we won't see any of those if we go to larger distances. But ALMA is not the right instrument to test that, and hopefully at some point we will have a dust continuous C+ survey telescope that could test this. But in the meantime, we are doing all this follow-up to try to understand these very targeted objects. And yeah, so what about JWST, right? So I think these are exciting times, especially now that with ALMA we are finding, well, we know these objects exist, they're spectacular, but now with ALMA we're observing for the first time the cold dust of the galaxies, but until now we haven't been able to see the stellar light of these objects because the central source outshines the galaxy, lower wavelengths, and even with HST we haven't been able to see the stars of these objects. And I really hope that, well, I really think that with JWST we will finally be able to do that. And also these systems that I just showed you before, these companion systems are really interesting. As you can see here, this square here is just the near spec IFU in James Webb. So one pointing, you can get an IFU spectrum every pixel of a very distant quasar at wavelengths that we haven't even tested yet, but also of a galaxy that we don't have any evidence of having an AGN so far. So two very distant galaxies for the price of one. So I'm really excited, really looking forward to cycle one. So let's go back to the last point. You don't have the minutes? Yeah. Okay. So yeah, now I'm going to change gear, move to the last point. So I showed you this at the beginning, again, epoch of reionization. One is neutral, zero ionized, and this is the best observational constraints we have. And I told you that quasars have been very fundamental on putting constraints on the end stages of reionization, and that's because we see this completely absorption flux blue of lemon alpha. That's the computation trough. But to absorb that flux blue of lemon alpha, you need actually a tiny fraction of neutral hydrogen, like 10 to the minus 4 of neutral hydrogen fraction, and then you can basically absorb everything blue of lemon alpha. And that's why till now, quasars have been only able to prove the end stages of reionization because otherwise it saturates. But I think there are still promising venues to exploit quasars and put constraints even well within reionization. And this is again not new. So this is known as the IgM damping wing. It's been known, it's physics known for more than 2 decades. Let me just walk. This is more or less complicated. So I have several slides to explain this. This is an example of a quasar versus 7.5 because we can, but this is an absorbed continuum, right? So this is like the quasar in its rest frame. And I'm going to zoom in to even more to the Lyman alpha region. And the thing is, yes, so when you have a tiny fraction of neutral hydrogen, you basically absorb everything here. But now if the universe is significantly neutral, so more than 10%, you also start to observe not only blue dwarf Lyman alpha, but red dwarf Lyman alpha, because Lyman alpha is a the scattering resonant line, right? There you go. So when the universe is very neutral, you start to observe even red dwarf Lyman alpha, for example. So the red was the intrinsic spectrum. If the universe was 10% neutral, 50% neutral, 1% neutral, then that shape will change, as you see here in blue, green, and yellow, and has a very particular profile. But again, so important is that you observe even red dwarf of the red frame Lyman alpha, and that's very difficult if you don't have a very neutral intergalactic medium. And of course, you can think a little bit about this and then try to reverse the experiment. So you go, you find the quasar, measure the profile, and try to infer what is the neutral fraction in that particular region, and you have a number. So in principle, this is that easy if you know how the intrinsic spectrum of the quasar is first, and if you see this profile. And until now, we haven't exploited this because we haven't seen this particular profile in these quasars, basically almost never, especially redshift 6. But there are claims that maybe we have actually already detected this effect in the previous redshift record holders of redshift 7.1. So there is some evidence that this quasar redshift 7.1 is showing this Lyman alpha damping wind. There's been some debate in the literature, but I think there's still some, it's not very strong, but I think there's still some evidence here that this exists, and this is complicated again. So what I'm showing here is transmission. So this is the intrinsic quasar spectrum divided, so a model of the intrinsic quasar spectrum divided by the observed, and this really depends how you model the intrinsic spectrum. So that's the debate, but I think we know how to do a decent job of that. And if you believe that we are measuring a real IgM damping wind here, this is very powerful because based on this one object, you can put a constraint like this in this diagram, right? So this tells you that based on one object, you can actually improve this. And if you find more of this, you should see a more clear tendency. So, but I've looked more than 100, maybe 200 spectra of quasars, redshift 6, 6.5, 6.9, and never seen something like this profile that is predicted until I saw this object here. So this is a quasar redshift 6.4. This is just now this is flux, so there's no model here, just showing the flux and masking some absorption systems. But this profile is very uncommon. So you see here that looks very strange. And this is exactly like an IgM damping wing, but it's very surprising. Yeah, I was knocking my head like a few weeks because I couldn't believe it. Right, so it's redshift 6.4, so this is 100 million years after redshift 7, and 15% of cosmic time at that age when changes are happening very rapidly. And of course, there are other possibilities for this. So the IgM is not the only neutral cloud that can cause this. So you can have a damped Lyman alpha system, so a DLA, just in front of the quasar that causes a similar profile. And that's also a valid explanation. And I think in this particular case, I'm very convinced that this is the best explanation, because then I took a fire spectrum, so near infrared spectrum, and we see several metal absorption lines at the same redshift where you expect this absorber. So in this particular case, I'm convinced we're not seeing the IgM damping wind. We just have a galaxy in absorption, or a low mass galaxy in front of the quasar, which might sound disappointing, but I think it's really exciting because we're seeing now a very low mass galaxy 800 million years after the Big Bang, where we can, for the first time, measure a metallicity and also relative abundances and see if we see signature of population 3 stars, right? So I tried to do that, but I didn't find any strong indication that we're seeing population 3 yields 850 million years after the Big Bang, and this one object. So what is clear from this is like a redshift 6, 6.5. We are not seeing the predicted IGN damping wind. We still don't see population 3 yields. So maybe we need to go to just higher redshift. So if we want to improve on this and constraints of reionization and population 3 nucleosynthesis, we just need to push this farther away. And as I already told you, this is not updated. So earlier this year, I found this quasar, which is 7.5, using Fire and Magellan, but this spectrum here is a combination between Fire and Ginners. It was a DDT spectrum. And I'm gonna go back to that. But so this is a very bright object that when the universe was 10% younger than our redshift 7.1. We also have a very bright C+ detection. And we have many other follow-up programs coming on. And you might, well, you can ask me maybe after the talk other offline questions about this object, but you might be asking now, well, I will be talking about this damping wind. Now we have this quasar, which is 7.5. This was based on one quasar. Do we actually see this signature in this object? It would be interesting either way, right? If we don't see it, it would be very, very interesting. And we see it would be even probably more interesting. I'm going to tell you that I think we see a very strong signature, but I'm going to let you read the details in the paper that will come very soon. And just go back to this, so the same spectrum, but I'm just going to emphasize that this also is, again, very bright. The most distant object we know, black hole that we know, 690 million years after the Big Bang. So when I took the discovery spectrum of this object, so I took it with Fire, so near-infrared spectrograph of Magellan, and the data was actually quite good, but Fire, to my surprise, couldn't go beyond 2.3 microns. Like then the sky in Las Campanas is just too difficult for Fire to get that spectrum. So then I called here my friends at Gemini and said, well, we have this quasar, and we don't know the mass of the black hole, which is one of the most critical properties of this object. And Ginners, in 4 hours, 4.5 hours, has a very nice spectrum of the magnesium 2 line, and that allows us to measure an 800 million solar mass black hole, or 7.5. So Ginners have been crucial to the characterization of the 2 most distant quasars known so far. And when you put this in a plot like this, so these are all real data. So these are masses measured from some of the most distant black holes. So this is the previous redshift record holder. This is the new one, both measured with Ginners data. And one of the questions that puzzle theorists for many time now is how to form these objects, right? So you have all this mass, 10 to the 9 solar mass black holes, and you need to collect that mass in less than 800 million years old, less than 800 million years. So that's really difficult. And you can see that this is difficult because if you make these objects accrete material at the maximum rate, so the Eddington rate, they should grow like this. And even for redshift 10, or you need very massive seeds to, if this is how these objects are forming. So people have tried to put some alternative scenarios, but the thing is, these are still a puzzle. And when we push this farther in redshift, we put even stronger constraints. And I think that one of the most promising ways to tackle this issue is to try to look, we know this object exists, and we know that there must be progenitors. And we should try to find the progenitors that are redshift 9, 10, with 10 to the 7 black hole mass. That's impossible with the current facilities. It's gonna be really, I think, possible even for JWST. And to do that, ELTs would be great. I think to find the progenitors redshift 10 of these objects, we need to wait for the ELTs.
So how massive are the objects at 10 and 11 that are found with HST? Are they lower than that?
We don't know. So the ones that are found at 10 and 11,
Yeah.
they are not AGN as far as we know.
No.
And people, so I don't have a slide here, but what they find is basically Lyman alpha line.
Right.
From the Lyman alpha line, you just can know star formation rate and not much else. So they don't have black hole mass measurements of those objects. They might be AGN, but we don't. To measure the black hole mass, you need to see the line.
Well, there are
but-
black holes, as you say.
But you also need to know the continuum pretty well. And basically, we don't have much of continuum emission of objects above redshift 7.
Right.
So I'm going to end up with this summary. So I hope I convey the message that we have made huge progress in this field over the last few years. We have more than 200 of these very distant quasars. And there are still many puzzles. Some are very old, right? So since their discovery, we know there are some objects are radio loud, radio quiet. I didn't even talk about that in this talk. But now there are new puzzles too. So we have this ALMA observation that shows that maybe these objects live in very strange environments. We have metal enrichment, so there are black hole growth. And I think this is just the beginning of the full characterization. I'm really looking forward to push the capabilities of ALMA that I think we are only starting by now. And of course, using JWST and the next generation of telescopes. And just want to finish to remind you that now we are able to push detailed studies all the way to redshift 7.5. So that was when the universe was 5% its current age. And this object is so bright and it's so evolved that I don't think is the first quasar ever formed. And I think we will very soon find more. Thanks.
Questions for the speaker?